A modern manufacturing cycle generates physical chaos. Every time a robotic arm articulates, it throws off continuous waves of vibration, heat, and acoustic data. Simultaneously, other systems operate at a completely different rhythm. A facility's photovoltaic array, for example, produces a low-frequency, steady trickle of voltage and current telemetry to monitor grid load. Contrast that immediate trickle with the facility's optical quality inspection systems. These cameras capture high-speed spectral arrays, generating massive, dense visual files to identify microscopic manufacturing defects. This diagram visualizes the severe disparity in data volume. Standard SCADA telemetry might require a bandwidth of just 10 kilobits per second. Meanwhile, the optical feed overwhelms the network with sustained throughputs around 94 megabits per second. The core engineering challenge of the industrial Internet of Things is capturing these vastly different physical modalities on a shared, constrained network. If the design is flawed, the high-volume data will bottleneck the system, destroying the real-time determinism required to keep machines running safely. Solving this requires a structured approach to the modern IIoT stack. We have to build the architecture from the ground up, starting with raw physical capture and moving sequentially up to edge intelligence. Facility automation relies on mastering this multi-layered architecture. If the data pipelines are properly managed, the facility runs continuously. If they are ignored, the system paralyzes under data congestion and extreme cloud latency. The foundation of this architecture is Layer 1, the modality and sensor plane. This is where physical realities are converted into electrical signals. Capturing accurate condition monitoring data requires matching the sensor to the physical behavior. Acoustic and vibration sensors, like accelerometers, require continuous high-frequency sampling simply to characterize the mechanical degradation of rotating machinery and high-pressure pumps. Environmental sensors expand this footprint outward. Facilities use laser-ranging depth sensors and multi-sensor rain gauges to monitor outdoor material handling and terrain conditions. Physical sensor deployment does not guarantee data integrity. Commercial out-of-the-box factory calibration for low-cost environmental sensors consistently falls short of the accuracy required for operational use. This chart shows how that inaccuracy is corrected. Engineers must conduct explicit laboratory and field evaluations to determine the error margin, then apply a mathematical offset to shift the factory baseline up to the true measurement. This rigorous approach to physical capture is now extending beyond machinery. Layer 1 increasingly integrates biomedical and wearable sensors directly into factory operations to monitor worker safety. Portable emergency systems actively track human health metrics. During incident responses, these wearables provide real-time reporting of a worker's blood oxygen saturation, body temperature, and heart rate. Tracking these vital signs requires no specialized infrastructure. Human telemetry relies on the exact same hardware components and connectivity patterns used to monitor industrial pumps and solar arrays. At Layer 1, the subject, whether a high-vibration turbine or a factory worker, is irrelevant to the architecture. The task is strictly about standardizing chaotic physical inputs into reliable, calibrated digital streams. Once those digital streams are generated, they move to Layer 2. Here, engineers must avoid a critical architectural anti-pattern, attempting to route raw, uncompressed measurement data directly from the sensors to the cloud. Pushing raw, high-frequency data directly to a central server introduces severe latency and exhausts network bandwidth. To clear congestion, we introduce smart edge nodes. Positioned between sensors and the network, they execute local preprocessing and filtering. They compress organized packets into a highly efficient stream. To prove this architecture works under extreme stress, researchers tested a commercial off-the-shelf edge setup against high-speed optical data acquisition. The local hardware was tasked with capturing 100,000 1-megapixel images running at a frequency of 23.5 MHz. The off-the-shelf platform successfully processed a sustained 94 megabytes per second with zero data loss, matching the capacity of specialized, highly expensive industrial hardware. With careful data acquisition design and localized multithreading, low-cost embedded platforms comfortably handled the latency-sensitive, high-capacity demands of heavy manufacturing. With the data filtered and compressed at the edge, Layer 3 defines the connectivity and topology. This layer governs exactly how the package data routes across the facility. There is no universal protocol. Selecting a communication method is a strict mathematical trade-off between the latency a machine requires and the available facility bandwidth. For remote deployments where wired networks are impossible, engineers rely on lightweight publish and subscribe protocols, specifically MQTT. Paired with standard GSM cellular or Wi-Fi links, it balances simplicity with interoperability. A recent photovoltaic SCADA deployment demonstrated the efficiency of this specific low-bandwidth topology. The open-source prototype consistently achieved average latencies of less than 2 seconds over standard Wi-Fi and under 5 seconds over remote GSM links. Operating continuously for 20 days, the architecture maintained visual load monitoring and electrical telemetry seamlessly, even persisting through downtime on the back-end cloud server. However, that acceptable 2-second latency becomes a catastrophic failure if the requirement shifts to time-critical actuation and closed-loop control on the factory floor. Relying on a cloud server to execute a round-trip command for immediate mechanical braking introduces network jitter. If a packet is delayed by milliseconds, the machine damages itself. This diagram shows the topology for closed-loop control. The sensor, compute node, and actuator operate in a tight, isolated loop to minimize latency, completely bypassing the cloud. The cloud asynchronously receives non-critical aggregated data to run heavy predictive model training without interfering with operations. Intelligent network topology protects operational integrity. It deliberately decouples the split-second demands of physical machine control from the heavy computational requirements of long-term cloud processing. This 3D blueprint maps the complete integrated IIoT architecture we've built. Down on the floor, massive, high-bandwidth optical data is intercepted and kept strictly localized at the edge node, executing instant machine vision inference for quality control. Meanwhile, lightweight supervisory telemetry from the factory's power grid is routed efficiently upward via MQTT protocols directly to the cloud. Once there, that telemetry powers critical analytics. Engineers apply mathematical techniques, like least squares estimation, to the supervisory data to quantify pump performance and detect mechanical degradation trends. This architecture succeeds by isolating computational complexity and placing intelligence as close to the physical sensor as possible. Deterministic, industrial-grade operational visibility is no longer restricted to a handful of expensive, proprietary hardware ecosystems. By implementing optimized data acquisition, rigorous sensor calibration, and edge-first network topologies, engineers accurately map physical reality into a powerful real-time analytics engine.